next relationship that we'd like to take a look at would be the relationship between pressure and temperature. Well, in this case, the third variable, volume, is going to be held constant. So in this case, we're actually going to see the size of the container is what's going to remain constant throughout our little experiment. So here's our experiment, and again, the volume of the container is what's going to be held constant. So I really want you to concentrate and focus on the particles themselves. What we're going to manipulate is the temperature. So what you will see is that the speed of the particles is actually either going to increase or decrease. And then what we're trying to observe is how the pressure responds because of that change. So remember, pressure we can see by watching the number of strikes against the side of the container. So let's see this in motion. So we're going to take a look at a couple different temperatures. Right now we're at 25 degrees Celsius, which is just about room temperature. You can see your particles moving inside of the box. Now let's switch it up to 100 degrees. Notice how much faster those particles are moving and what's happened to the pressure. It's much bigger. And down at the bottom, you can see that we have some axes and a graph is actually starting to form. Here at ice water, it's much colder. The particles move slower. They hit the sides of the container much less frequently, and down at negative 78 degrees, it's even worse. Take a look at that relationship. It is very linear, kind of interesting. And as you notice, the pressure increased with increasing temperature, and the pressure decreased with decreasing temperature. Well, in my mind, what that means is that pressure and temperature are directly related, and that means we can develop two different styles of equations. The first one would be a constant equation under non-changing conditions. In this case, the pressure divided by the temperature would give you a constant. And that allows me to develop my second equation under changing conditions. In this one, P1 divided by T1 will equal P2 divided by T2. So the original pressure divided by the original temperature will equal the final pressure divided by the final temperature. And this can be extremely helpful mathematically. This relationship is known as Lusac's law. Let's look at an example problem. Now in this problem, the first thing that I notice is that the problem is talking about a rigid gas cylinder. And before we talked about that being kind of a code for the volume in this problem is going to remain constant. That's a really good hint that in this case you're going to be able to apply Lusac's law under constant volume. So let's keep reading. A sample of a trapped gas has a temperature of 150 Kelvin and a pressure of 1.5 atm. If the temperature is raised to 250 Kelvin, how will the pressure change? Again, because we're dealing with pressures and temperatures, but we're dealing with constant volume, that's going to allow me to use Lusac's equation, which is P1 divided by T1 equals P2 divided by T2. Just like before, let's go through and define our variables. So the first number that I see is 150 Kelvin. I'm going to label that as T1 since it's the first temperature that I see. I also see 1.5 atm, and that's the first pressure, so I'm going to label it P1. Then I see 250 Kelvin. That's the second temperature that I see, so it's T2. And finally, the problem is asking me for the pressure. And since it's undefined, I'm going to give it an X. Now I plug my variables into my equation and solve. And I notice everything has two significant figures in it, so I'll leave two significant figures in my final answer, which gives me 2.5 atm. Unless it was a little unclear about the graph before, let's see that one more time. Again, it's a very direct relationship. And the data that's actually up on the screen right now is the data that we can typically get under normal laboratory conditions. Not every temperature we can actually reach in the lab, but the ones that are provided here are pretty decent. Now what bothers me is it's only a line segment. I really like it when the line continues on. And I'm kind of curious to see where it actually would cross the x-axis, since that's at temperature. And what I see here is if I would continue my line in a linear regression, I notice that it actually is going to cross the origin, which is actually pretty neat. Now what that implies is that the temperature at which you would have absolutely zero pressure is 0. 0 on the Kelvin scale, that's a very special temperature. It is known as absolute zero. And for this set of experiments, we're going to define that as the temperature at which a gas has absolutely 0 pressure. Unfortunately, what that implies is to have 0 pressure, the gas particles can't strike the side of the container at all. That implies that they have to completely stop moving. I don't really think it's possible to completely stop a gas particle from moving. So unfortunately, what that means is that absolute zero right now is an impossible temperature to reach. I think it also might be helpful to have a real-life example of this law in practice. And the best thing that I can think about would be tire pressure. Now, your tire is essentially a rigid container. Its volume doesn't necessarily want to change. But we expose it to a variety of different temperatures and riding conditions depending on where we live or where we're visiting. So I know that we can drive through the snow, which is extremely cold, and I know that in the winter time, the tire pressure tends to be a little bit low at these low temperatures. But then we also drive our cars in the summertime, and with those increasing temperatures, the tire pressures can also increase. So as a method of safety, we should usually check our tire pressures before we go out driving. I have another example in the next video, which I think you'll enjoy.